My sister has this absolutely awesome habit of riding towards me on her bike as fast as she possibly can and then braking at the very last second. So, if I see her riding her bikes towards me, how long do I have before I should get out of the way or tell her to brake? Let's take a look at how the kinematic equations can help us answer questions like that. Welcome back to Fast Physics, where I learn things about physics and put them in short videos for you guys. Today we're going to be looking at how to use the kinematic equations after learning how to remember them and learning how to derive them in my last two videos, which you should check out if you haven't seen yet. So how do we use the kinematic equations? Remember that they are equations for motion in one dimension where acceleration is constant. Well, one of the easiest things that we can do is first to write them down. So if we take a look at our kinematic equations, we can think of them in terms of what variables they have and what variables they don't have. The four variables that are involved in the kinematic equations are velocity, acceleration, time, and displacement, or v, a, t, and x for delta x, which is displacement. So when we look at each of our kinematic equations, they're always going to have one of the variables missing, leaving them with three each. This first one has velocity, acceleration, and time, but not displacement, so it's the VAT equation. This one has acceleration, time, and displacement, so it's the tax equation. It also does have initial velocity, but it's missing final velocity. So the V isn't in the acronym to remind you of what's missing. This next one has velocity, acceleration, and displacement, so it's VAX, where time is missing. And finally, this one has velocity, time, and displacement, so it has the incomparable acronym of VTX. Obviously, acceleration is missing in this one, and it's the only vowel, so that's why it's so lovely and unpronounceable. When we get a problem, the first thing that we can do is look to see which variables are there and which variable isn't there. That helps us to choose which equation to use. If a problem gives us velocity and acceleration and tells us to look for displacement, we know to use the VAX equation, where time isn't mentioned at all. Conversely, if the only variable that a problem doesn't mention is, say, displacement, we know that x isn't in the acronym, so we must be using VAT. Let's use that scenario from earlier to try and use our kinematic equations. So let's say that my sister spots me when she's 7 meters away from me, and she immediately begins accelerating towards me at a constant rate. She was already moving at 5 meters per second before she started accelerating, and by the time she gets to me, she's at 10 meters per second. How long should I wait until I get out of her way or tell her to brake? Well, what variables can we see in the problem? We have 7 meters away, which is our displacement, 5 meters per second before accelerating, which is our initial velocity, 10 meters per second, which is our final velocity, and how long, which is time. Since the only variable that we aren't explicitly given is acceleration, we know to use our VTX equation, or final plus initial velocity divided by 2 times time equals displacement. So once we know that, we can substitute the values that we know in our equation. So that's 7 meters, 5 meters per second, and 10 meters per second. Now all we have to do is solve for our last variable, which is time. 5 plus 10 is 15, divided by 2 is 7.5 meters per second. We divide both sides by 7.5 to isolate t, to get that time is 7 meters over 7.5 meters per second, or 0.9333 seconds, after the meters cancel out. If we round that to a specific number of significant figures, which I covered in my second and third videos, we get 0.9 seconds, because all of our measurements has 1 sig fig each. So I should be getting my butt out of the way sometime in those 0.9 seconds before my sister hits me with her bike. One of the easiest ways to check our work is just by checking that our answer looks reasonable. Use common sense. We can do that by looking at the units of our answer and making sure that they match up with what we were looking for. We also can check that all the magnitudes in our signs make sense. In our original problem, we were looking at how long I had to get out of my sister's way. 0.9 seconds sounds like a reasonable answer for how long, since it's an amount of time, and we can look back in our work to check that we cancels out all the other units properly. Spoiler alert, I'm pretty sure that we did. But if we'd gotten an answer like 0.9 meters per second squared, which isn't even an amount of time, that would be a big clue that something was wrong with our calculations. Who says you have 5 meters per second squared until you have to get out of bed? In the same way, answers like negative 0.9 seconds or 900 seconds wouldn't have made sense in the context of this problem. Time, as far as I know, doesn't run backwards, so our answer couldn't be negative, and what are the chances of my sister being so slow that it takes her 15 minutes to ride 7 meters towards me on her bike? Now, if you don't trust your common sense, or if you just don't have any, which is always me, you can also check your work in other ways. You can always just plug your answer back into your original equation with all the other variables that you know. If we do that with the problem that we just solved, we can bring up our VTX equation again and substitute all the variables. Remember that if you rounded an answer, it won't work in the equation. You should use your original answer. So if we plug all our numbers in with 0.9333 instead of 0.9, and solve both sides, we get that 7 meters equals 7 meters, which is true and tells us that our answer was right. So what happens if your common sense tells you that an answer is wrong, or if you plug your answer back into the equation, and the two sides aren't equal? Well, you should check over your work to make sure that you canceled everything properly, and you followed all the correct mathematical rules. Maybe you didn't add something to both sides of the equation, or maybe you didn't see a negative sign. If none of that seems wrong, then you might have chosen the wrong equation, or misread the question. You might be missing a term that you need for the equation that you chose, and would be better off using another one. Or you might have just misread the direction of the velocity in the question stem. But I promise that none of the practice problems that I've attached are trick questions. They should all work out properly, and I promise that the answers that I give you will be reasonable. If you have any questions, feel free to ask me, and I'll try my hardest to answer all of them. Thanks for watching this video, and be sure to stick around for my next, which will be about freefall. Bye!